All right. All right. All right. All right. Believe we are good to go. There's always delay. There's always delay. There's always delay. There's always delay. We'll get the name. We'll get the name. So I'll get anyone that is. 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 How about now? Now, OBS has a mind of its own. Fixed, gone, great, good, awesome. Thank you very much for that. So I have to reconfigure OBS every time that I stream because it forgets what a camera is, it forgets what a microphone is. You've probably seen me do it in class. But my voice is a little bit, I can feel it in my throat because I try and project in class. I'm not actually trying to yell at people, although I could see how people could think that. And it was worse last night, so I didn't record anything. So for anyone that is just catching the stream for like the first time, this is pwn.college. These streams are a kind of series of lectures and discussions on how to hack. If you're interested in learning this stuff, you can go to pwn.college, create an account, and kind of follow along. It's free and open to anyone that just wants to learn. This particular stream follows a university course, and so if I go up to dojos here and scroll down, we are talking about CSE466 for the fall 2024 semester. The topic that we are currently discussing is program security, which is kind of a catch-all here, kind of a review for things that were described in an earlier course. So we're going to kind of take a look at shellcoding and memory corruption. With that, the way that I kind of do office hours is quite open-ended. Feel free to throw questions over in the Twitch chat, at least when I'm streaming from my home office here. I can certainly see Twitch chat, so we don't have any problems because I have multiple monitors, unlike when I'm on campus. Right now, I see just the audio comments. So if somebody does have something in particular that they wanted me to go down and explore, I'm more than happy to do so. While I'm waiting for the Twitch delay there, the one thing that I would like to do, that I intended on doing in class, we just didn't. I have a mood light, believe it or not. It's actually quite dark in the Rob cave. One thing that I wanted to do that I didn't really get time to because we didn't end up there was I wanted to use the tools that we were taking a look at in class and just talk about writing assembly in general. After class, somebody asked me about there's one of the challenges, I'm not sure which one here. So 5 says you can't use the syscall instruction. You can't use int or int8, which would be the 32-bit version of how syscalls are performed. So how do we perform a syscall without having a syscall in our shellcode? This one looks like a similar type of check. This one closes all file descriptors. One of these says that you have to use unique bytes. Okay, here it is, level 12. Write and execute shellcode to read the flag, but every byte in your input must be unique. And that's that's a little bit harder to do. I showed some tools to iterate on it, but how do we think about that? Well, we use the tools. I do see the comment here in Twitch chat. That says, it's not specific, but hey, can we talk about canaries, memory errors? Yeah, I'm more than happy to spend some time there since I haven't gotten there, at least in what I'm discussing. But I will touch on that at some point in the office hours here. And then despite the voice, this is better than it was last night. I'll record and get something up this afternoon, like right after this stream. So when we're talking about like unique bytes, we're going to do something similar here. We're going to say shellcode equals ASM. Keep going here, and we'll print the disassembly of the shellcode. And let's actually do something here. Let's do, what do we want to call? Let's call open. We'll call open. So if I want to call open, man to open, this is the syscall that I want. These are up here at the top, the arguments that I have to set, but the man page will not tell me what is the syscall number here. So to get that, we ask Ryan A. Chapman. We look at his amazing syscall table. Open, RAX needs to be 2. So let's just quickly stub this out. One of the things that was asked on the Discord is how do I do comments? As long as you terminate your assembly here, you can put like a C-like syntax for // and then have a comment. So if that helps you as you're kind of writing it out to understand what you're doing, you can certainly do that. If it is the beginning of a line, you don't need to have that terminating semicolon. So our first thing that we're going to do here is call open, right? This is our goal. So we're going to move RAX to 2. Then we need to start setting up these registers and these arguments for open. The first thing that we need here is a pointer to the string. I'm going to put something on my, let's echo secret stuff into, I'll call it some file. And so the full path for that is home hacker some file, right? Now I need to get these bytes somehow pointed to. Now, in class, I showed that we could, if we had something short, we could just push some raw hex, right? We could push it to the stack, and that can get it into memory. But here I have a path that's quite long. Now, there's more than one way to just get bytes into the stack, and I'm going to try and use different techniques at different times just so you can see different ways of doing this. One of the things that people often kind of run into in this class is there's more than one way to do things, and honestly, I don't mind which one you use. If somebody starts down one path, I'll try and continue along that path, but there's many ways to get it done. If it does get done, you're doing it right. One of the questions on the Discord last night that I responded to was about having a data section. And there is no data section when we're talking about shellcode. But we can do something very similar here. At the end of my shellcode, I'm going to pretend that I have a data section. I'm going to treat this part of my shellcode as if it was a data structure. And so I'm going to make a label. I'm going to call it path. And we are going to have the dot string is a pre-assembler, I believe, pre-compiler. I think it's an assembler directive is the correct term. But there's a number of kind of magic keywords that you can include in your shellcode, and these tell you or tell the assembler what it is you're trying to do. So I'm trying to just declare a string here, and I want it to be home hacker some file. Recall that this is a label. A label means something to us when we're looking at the assembly, but the way that it actually gets wrapped up after the assembler parses it is it just turns into some relative offset. Now, what I really want to do is I'm trying to get this path name into open. I'm going to use LEA, which is for load effective address, RDI, then I'm going to say rip plus, not string, plus the label. So this path right here is referring to this label. We'll see what this looks like in the running assembly as far as the bytes. Somebody in Twitch chat here says you could also consider using push and pop or push and pop in level 4. And that works. So I could get a string as well into the binary using push and pop. The thing to keep in mind with push and pop is I can only push at max 8 bytes at a time. And in this instance here, the path that I am pushing is more than 8 bytes. So I would have to push multiple times, and I would have to deal with the sub-problem of in what order do I push these. Yeah, Twitch says they're replying to something else in the discussion. That's fine. I'm going to try and sync things in here and relate them back and forth. Pushing is 100% a valid strategy for level 4. And I think is what I would encourage, doing like a push pop. All right, so we have that. The next thing that I need to do is I need to set the flags and mode. Now, we don't necessarily know what this flags thing is. I'm over here in a man page. If I hit slash, we see it down here in the bottom left of this pane. I can search, so I'm going to search for flags, and then I can hit N. I'm just looking for where in this documentation does it tell me what flags are, right? We have to make sense of this. And right here up at the top, it says that the flags must include one of the following access modes: O read only, O write only, or O read write. You probably dealt with this in 365. Like I said, this largely should be kind of a bit of a review, but if it fell out over the summer, we can get there. So how do I find out what O read only, O read write, what these things are? Because I can't use these literal things in my assembly, right? They only exist in the C context. Well, I can again use pwn tools. So from pwn import star. Pwn tool is exposed to something called constants. It's just kind of this magic global. And I can say constants dot, and then start typing out the name of what I'm interested in. In this case, O read only. And if I just hit that, we get constants O read only has a value of 0. If I was interested in, which isn't particularly interesting, but like write only has a value of 1. It's pretty common for these constants to follow that pattern of 0, 1, 2, 4, etc. However, it's not a good thing to assume because you may end up having other problems. There are other ways to get those numbers. I find this to be a pretty easy way that works 9 times out of 10. So now that I know that read only has a literal value of 0, let's set up RSI. I'm going to move RSI 0. And then the last thing that I need here is mode. Now, mode, if we search this man page here. Okay, it says the mode argument specifies the file mode bits to be applied when a new file is created. Well, I'm not doing O create or O temp. I'm not creating a file, so this mode thing doesn't really matter. So I'm just going to assume, based on the documentation, that this doesn't really apply because of what I'm doing, and so I'm going to set RDX to be 0 as well, just to be sane. Okay, that is a side chatter, which is good. Like, feel free to ask whatever. I will jump back and scroll through it when I get to it. All right, so I have that. The last thing I need to do is perform a syscall. I'm going to add some comments here. Load a pointer to string or to path in RDI. This is the O read only. This right here is the mode, which shouldn't matter. And then we need this to trigger the actual syscall. So essentially done something where I'm treating like I'm acting like I have a data section, right? But what's going to happen is the same thing I described in class. When the instruction pointer after this syscall is executed, the CPU doesn't know that the stuff after it is not valid x86. And so what it's going to do is it's going to just march forward, and it is going to try and interpret /home/hacker/some file as instructions, and it will blow up. And we can see that real quickly here. Oh, what did I fail? I failed my boilerplate. So I just to scroll up so you can see what it was doing. The error here is coming from the assembler. It says ambiguous operand size for move, too many memory references, ambiguous operand size for move. The reason is I didn't set my context. You told me not to forget to set my context. You know, sometimes it's a good thing that I forget things because other people will forget it as well. And so it's a nice refresher there. Oh, it's not run shellcode, it's debug shellcode. Damn. Sweet. So another kind of magic Pwn toolsism. Much like how we had debug assembly, which took the literal assembly, there is a complementary command debug shellcode that takes the raw machine code bytes. In the end, we're doing the same thing. All right, so here I am. I'm at move RAX2. We can step. Now, this is that LEA where I had kind of that magic with the brackets and rip plus string. Right? That's where I had this right here, rip plus path. The label, after it goes through the assembler, turns into a relative location, which is what we see here in the debugger. It's saying load whatever is at RIP plus 16. And GDB is nice enough to give us a comment here to kind of tell us what that resolves to. And that resolves to right here, which we see is a bad instruction. But if we were to examine that location as a string, we see that it has that home hacker sum file. So I'm kind of abusing this region of memory that is intended to have executable instructions and throwing stuff that is not instructions in there, knowing that it will blow up, but it will blow up after it does what I want. So let's step through and see if I got everything else right. So we do this LEA, and then if we were to quickly here print RDI, and then examine the string at RDI, it does do kind of what I was claiming we'd do there. We set both of these to 0. We trigger the syscall. I want to know, was that successful? We will print RAX, and we see 3. Open, for those that are not familiar, returns a returns a file descriptor, which should be a constant int. One of the common patterns that you could look for when you're parsing these man pages is you can look for a section near the bottom by searching all caps for return. You'll find return value. This gives you kind of a synopsis of what you expect to happen. And it says open and similar calls here, return the new file descriptor or -1 if an error occurred. Well, I didn't get a -1 in RAX, which means my open call was successful. So that shouldn't be anything like mind-blowing there. But I want to use this as a toy example to say how else can we set these things up? What if I wanted to do this without how else without using H-bytes? How could I do that? Right? And it turns out everything that I just wrote here, every single one of these instructions, aside from even the syscall, every single one of these, we could change them to get the same thing done. Question from Twitch here. What if what if you want to hold variables and not constants? I'm not sure what you're asking. Reading into a buffer. What if okay, so like if I was calling read, could I still use this pattern? I think is the question. Like if I wanted to read into this memory location, could I use LEA to reference something that is after my shellcode? The answer is yes. So I could just as easily say, this is some buff, right? It doesn't matter what I call it. And I just so that I have something, I'm going to put a NOP there because I think the assembler will be grumpy if I just have a label with nothing. And I could if say I was calling read, I could call LEA, RSI, RIP plus some buff and read into this memory location that is after my shellcode as well. You don't have to use the stack, but the stack is, for those type of things, the stack is typically what you'll see. Because this relies on wherever your shellcode is executing at the time of it executing that region of memory being writable, which on these challenges it is, I believe. Okay, no, it is for most of them. But the challenges that don't, as I'm thinking about it, the challenges that don't explicitly tell you what's going on there. Do you still need to open, read, and write if you use chmod? The answer is no. So if we take a quick look at chmod here, the arguments for chmod, the first one is a pointer to a path name. The second argument, I think in class, I was rewatching the recording, just kind of scrubbing through it to see how things went. And I said that chmod has one argument. That was incorrect. There are, in fact, two. The first argument to chmod is a pointer to a path. And the second argument is the mode that you want to set it to. You'll note that neither one of these arguments are a file descriptor. Calling open, the reason that we typically call open in shellcode or even when we're writing something in C is because we want a file descriptor. And that's one of the benefits of going down this kind of chmod route is I don't have to call open. I can just directly call chmod with a path name. Now, if for whatever reason you wanted to just write more shellcode because you're really enjoying it, we do see that there is another call fchmod, and that one does take a file descriptor, in which case to use this, you would need to call open to get the file descriptor, and then you'd call fchmod. Awesome. Wasn't sure if the permissions to read a file, I wasn't sure if it was only changed while that process was open. No, so if you run chmod, and I'm going to just do this here in the terminal, but we can see that it is a permanent change to the permissions of the file for the lifetime of that file system. So I had, I think, some file, what did I call it? Yes. If we lsl some file, we see this is read and writable by the hacker user, and then it's readable by anyone in the hacker group, and it's readable by anyone else that is neither one of those parties. If I were to chmod, what do I want? 600 on some file. This in the terminal, we spawned up, ran chmod quit, it finished its job and is done. And then if we take a look at some file again, we see here that it is now only readable and writable by the hacker user, and nobody else can read, write, execute, do anything with this file. So when you run chmod, those changes persist across time, right? It's a permanent change. Somebody says some assemblers accept constants like sys_chmod. That may be the case. I don't know it. I don't want to derail too far. So the default assembler that we're using here is the GNU assembler part, which is part of GCC. It uses a syntax called gas. If you're just Googling random things online, somebody mentioned to me, hey, I was reading about something called NASM. NASM is another style of assembly, or another like assembler syntax. We will not be using NASM in this class. There are different rules and things between the two. if you know NASM and want to rock and roll with that, you're welcome to do so. Although I will not be providing support for it. Yes, somebody here on Twitch says NASM is on the dojo. That is true. Like, you're welcome to do so. It's just I need to try and standardize on something, which is why I'm doing what I'm doing there. All right, let me scroll back up and see if there were any comments. Oh no, I have gone off the rails. Okay. Any comments before I continue down this road here? Push pop, that's good. Grab push pop, didn't know about constants. Okay, I think that was all the side conversation, so I think we're good there. So what if I wanted to run this, but I want to write the same thing, but I don't want to have any H bytes? Well, there's many ways that I could do this. Instead of, for instance, move RSI, I could move ESI. If I wanted to make RDX 0, instead of moving 0, well, let's do something else. Let's try XOR RDX. Is that going to get me 0? Yes. If I XOR something with itself, it'll be 0. Did that XOR? That XOR has an H byte in it, but you'll note that it's a lot shorter instruction. Right? Okay. Well, if I can't do that, what if I XOR EDI? Right? Now I'm working with 32-bit registers. Okay, cool. That would zero it out. Recall that anytime that you set a 32-bit register, it will zero out the higher order bits. So let's, over here, we're just going to have some scratch. The many ways to zero a register. And I'm looking for things that you think we could do. So I said we could, and we're going to say zero a 64-bit register. So I could move, I'm going to use RAX in the example here, but it doesn't matter. I could move 0. We said I could move EAX 0. And I also said I could XOR EAX with EAX. Somebody here says sub. So sub is something I could do. Should I be sub EDX, but sub EDX EDX, right? If I subtract something from itself, that should be 0. Sub EDX EDX, look, there's no H byte, and subtracting, it turns out subtracting X from X does in fact result in 0. Somebody says and 0. Okay, so we could do that. We could and something with 0. And that would do it. This one let's step through if you're not a believer. I have too many things up. Let's do this. All right. So we're going to get down to that and instruction. So if we look at EDX, or not EX, EDX, right now it is 0. That's no fun. Let's move EDX OX1337. Let's make it just so it has a value so that we can show that it is actually zeroing stuff out. And if I can type, okay. So we are about to and. If we take a look at EDX, it has a value. When we step through the and we print EDX again, it is 0. Because and is going to include only the bits that are in common with both operands. Or both, I'm going to say arguments. It might be operands. But so we can and EAX 0. Let's see, do I have any other ones here? Somebody says, I once Googled the most efficient way to zero a register, and Stack Overflow had a pretty good discussion on it. I don't know what is the like absolute most efficient way, but we can. I still know of a couple just off the top of my head here. I don't have like a secret list that I'm referring to. Yeah, multiple, as Twitch says here, multiple ways are important to know. Although sometimes there's no way, and you just have to pray. Like, you can end up in situations or constraints where like there's things that you simply can't do. But another thing that we haven't looked at is shift left or shift right. These are bit shift operations, and it turns out when you shift bits all the way to one side, they just kind of fall off into the netherworld. It doesn't wrap around to the top. And so if I want to shift the EDX register by 32 bits, what should happen here, we take a look at EDX. It has that value. When I step through it, that's RDX. What did I do? Shift left, EDX, hex 20. This is a thing. Let's consult the Googs. Bit shift, AMD 64. No. That's all Python. I don't want Python. Show me. SHL. What did I miss here? Operand. Felix, x86 SHL. Yeah, that's where I am. Register followed by a constant. Why did that not do what I thought it should? Debug the code live. Yeah. This is how you know things are live demos, right? Like, I feel like that should EDX, right? All right, I will have to think about that. Shift left. That should have done what I thought. All right, register 1 to be multiplied by 2. Oh, I'm shift lefting, right? That's shift right. Okay, so I want shift right, but that still should have. Okay, let's shift right, which is the equivalent of dividing it by 2 a bajillion times. So if I take a number, I divide it by 2 a bunch of times, we print EDX. All right, I'm going to pause there. Somebody says, why not shift right by hex 40? Because it's 64 bits. Yeah, but I'm bit shifting a 32-bit register, right? Like, even if we did this 64, right? I'm still getting that. Like something is amiss here. Like even just bit shifting it by 2, for instance, should modify this value, and it should be something strange. So let's. I'm not sure why that is behaving as it is. It's not doing the bit shift. All right. Context, arch, AMD 64, shellcode, ASM, move RAX 1337, shift right RAX because it's still just two arguments. Okay. Shift right RAX 64, and then we'll throw a NOP so that we have something there, and instead we will debug assembly. All right, that's before the shift. That's after the shift. Okay, I'm not sure why that is doing what I'm thinking, but you can bit shift. I printed before the shift. Step where before the shift we print RAX. We step again. We're at the NOT. We print RAX. We step again. We're about to explode. We print RAX. Yeah, so something is amiss there, but you can bit shift things out of existence. I'm not entirely sure what edge case is happening here. Sorry, that was a bit of a detour. So we'll just kind of leave that as a shift, as a mystery here. Shift left or shift right, bits out of existence. That should work. I don't know why it's not working right now. I'll have to think about that, and I will respond on the Discord. You want to blame Pwn Tools? That's fair. Like, it could be some weird Pwn Tools thing going on right now, but you absolutely can do that. I just don't want to waste more time on stream here doing this. So we see that there's a number of ways that we came up with right now to all do that, and if we were to look at the bytes of that by printing the disassembly of these various instructions, we would see that we have the opportunity to kind of permute these things and get the same job done without while changing the bytes that are the assembly instructions. Another example that I believe was kind of loosely referred to on the Twitch chat here is you can push a literal and then pop it off. So we step, we print RAX, it is some magic value. We push a 0, we pop it, then if I print RAX, it is now 0, right? So another strategy that we could employ is, for instance, a push and pop. It's two instructions where they're both small instructions, and they all get the same thing done. And so you have to be a little bit creative here in what it is that you're trying to do. Like, we could get even more weird. We could, for instance, divide EAX by EAX and then subtract 1. Because if I divide something by itself, this could get a... Although the divide instruction doesn't work like this. Read the documentation, now that I'm thinking about it. Divide EAX to get a 1, and then sub 1. There is also, instead of this subbing 1, we could decrement it. If we got something that's at 1, if we have something at 0, there's an inc to increment by 1. And so we see that there's a bunch of different ways to do things. And that is why the kind of initial focus here was on having something like this where I can quickly print out my assembly and see what is going on with the bytes as I have these different instructions. Because this will help you look at different ways to accomplish your goal. All right. That was what I wanted to open up with in class, was something like this. We just didn't... we rabbit holed real fast. Looking at Twitch chat here, does anyone have any questions on shellcode or a shellcode concept? Something is blowing up. Can I do this? A hypothetical. I'm going to give it a couple minutes or not a couple minutes, but like 30 seconds or so for the Twitch chat delay because you run like 30 seconds to a minute behind what I'm doing live over here. If there's anything that is shellcode focused, I want to kind of hit that now. If not, I'm going to circle over to the question that was, let's talk about some memory corruption stuff. So I have one question here that says, can I use ESP as the path pointer in chmod? That's a good question because the answer is no, and a lot of people don't understand why. So we can take a look at that. All right, to understand why ESP is not good, let's see, we have RDI, we have RSI, and then I want to move EDX 0, and this is for the mode. So I have right now some shellcode that is sane and we'll call open. All right, this should be we'll just verify that to make sure I'm the success of the call open. If I wanted to use the stack and play around with that, your strategy would be something like push. I'm going to use the power of the F string because I don't want to deal with figuring out the hex for this, which will be, yes, we will unpack, and I am going to say some file 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a problem. So if I wanted to get this whole thing up there, I need to 1, 2, 3, 4, 5, 6, 7, 8, 64, and then we're going to push. What do I need? Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8. Because you can only push 8 bytes at a time. That's why I'm like, oh no. Then I would want to push, and this will probably not work. As I'm looking at this. But it'll be a fun thing to take a look at. Okay, so I want to push my string onto the stack. In this case, I'm just pushing some file instead of the absolute path. And the reason, so there is a generic pack function that will let you pack and unpack arbitrarily long values. But that isn't useful for this right here, unless you're talking about a different macro, which there may be. Like, I do not know all of Pwn tools. I learn something new every time that I teach this material, which is great. It makes it fun. And so that should get me onto the stack. Let's run it and make sure it is not happy. Why is it not happy? It doesn't like the operand for push. Let's see. Let's make sure I'm doing this right. Okay. Oh, you can't push a 64-bit literal. I literally talked about this in class. You can push a you can push a 64-bit register, and you can push D words, right? Okay, so if I wanted to do that, I would need to get this into a register. So I'm going to use a 64-bit register, which would involve an H byte, but that's just because it's the quickest way for me to make this work. It turns out you need to have that comma. The comma is important. Okay, there we go. And so I have this magic thing that goes in the RIX, and then if we examine the string at RSP, I'm still in RIX. So then we push RIX, we examine the string at RSP, we get file, Now, I mentioned that you need to have a terminating null byte, and a lot of times that will be there. We see in this instance, I do not have a terminating null byte. The byte that happens to be after my E is a 1, which is a problem. And then if I look at my second push, and then we examine the string at RSP, well, we got S. Well, what happened? Well, let's look at like 4 giant hacks at RSP. Here's my S, and then I have a whole bunch of null bytes, and then here is file. Somebody says, can't you just move into EAX, then push RAX? So you can't do that. And the reason is you'll end up with something very similar to what I have right here. So EAX would consist of these first 4 bytes, these lowest 4 bytes, 1, 2, 3, 4. And then when you push RAX, you're pushing these 4 bytes plus a bunch of nulls. Right? And so you have to think about what is the order of arranging these bytes so that they're pushed and right next to each other. Since I have this long string, right? Since I didn't use a symlink and just say, my file name is A, right? I can and avoid it. I now have this whole other sub problem that I'm trying to deal with, which is fine, right? It's a good thing to think about. Now, what I really want is I want that S to be the highest order bit. So I believe, we'll see if I'm thinking about this right. I want 7 null bytes in front of it. Right, no, this is a byte string. I want 7 null bytes in front of it. So I can specify a null byte like so. Now I have this problem right here of file, and then the thing that's after the E wasn't a null byte. I'm going to solve that. I could solve that by shifting all of this back and then moving this O down to here and then including a null byte right here. Another way of solving that that is a little bit more straightforward, as long as you have enough bytes in your shellcode to do this. I'll just push 0 beforehand. So then I know that there's a 0 before I start pushing my string. What did I do here? B this, which the complaint F string cannot include a backslash. All right, Python, you be like that. We're going to call this, my S value is going to equal U64 of BX00 times 7 plus BS. And then in here, instead of doing it literally, we will just reference it as a variable. Cannot assign to an expression here. I can assign a variable. Variables exist, Python. What's going on? These are some strange things, unless somebody on Twitch is catching what's happening there. Okay, bad operand for push. I know I can push 0. Oh, I can't push a literal value. I'm doing the same thing again, so we'll move RAX, my value, and then we'll push RAX. Again, you can't push a 64 or a 64-bit literal. Even though I know it, you'll see me try and do it regularly. All right, cool. So we put the file into RAX. We're going to push a 0 on there. The reason that we push that 0 is so if we look, now I know that my stack has a 0 as the next thing. We push RAX. So then if I examine my, let's say like 4 giant hex at RSP, we see this is file, which we can examine the string at RSP, or examine the string at RSP. We get file that is reading from here up, and then it encounters this null byte. So that's why it terminates, and we don't get that weird /01 there, because now my string is null byte terminated. Now we're going to move that S in there. We push that. If I did my Indianness correctly, we get, there is no, the string at RSP is now nothing, right? But if we were to examine that same 4 giant hex at RSP, what I've done is my string doesn't start at RSP now, right? Because I had all those leading null bytes. My string is at RSP plus 7, which is a weird place to be, but you totally can use it. There is some file. Why plus 7? Because this is where the string RSP points to when we're dumping this out in GDB. If you have your kind of head wrapped around Indianness. And so this would be byte 0. I have to add 7 to get to this location right here. Now, and so by accessing RSP plus 7 as a string, we see that I do get that value some file. So you certainly can get things onto the stack. Now, in the context of not having H bytes, this becomes a bit messier, a bit more messy than that, because I can't use these 32 or these 64-bit registers. I have to use 2-bit register or 2-byte registers. And so that means when I am moving these things, this becomes something like, okay, move AX, push, and then move AX, and this wouldn't be 64, this would be a U16 because that's 2 bytes. Then I would U16 be FI, and I would have to do this 2 bytes at a time, or in 2-byte pushes to get them on there. The 2-byte pushes don't need to be padded with a bunch of zeros. You can just push a word directly onto the stack. Let's see what Twitch here says. Okay, you caught me. I had a dash in my variable name. Somebody says, if you can make the challenge read more, then maybe there's a way. That's a response to something earlier. Let's see here. For levels that are asking us to send like 12 or 6 bytes, some of these like reduced number of bytes challenges, is the only way to pass them is to actually send the shellcode that is only 6 or 12 bytes, or is there a way to send more than that? So I didn't include it because it's assumed knowledge from 365. So I didn't explicitly cover it, but somewhere, I think it's find the video. Yeah, you got way more videos for this module than you will in future videos, just because there was assumed knowledge, and so I included stuff from like 365. What you can do is something that's called 2-stage shellcode. And 2-stage shellcode isn't I know it's included in here. Whatever. I'll just show it instead of trying to find it in these videos. So 2-stage shellcode. That the idea here, and I'm not saying that this is the solution for both of these, because I don't think you can do it in the 6-byte one. But the idea with 2-byte shellcode is if you manage to get, I don't know if it's quicker to clean this up or just start writing fresh. If you manage to write shellcode that calls open, or calls read, which hopefully Ryan A. Chapman agrees with me. Read is 0. If I can call read, RDI is going to be my file descriptor. So let's just for reference for those that don't have all of this stuff memorized. Our RDI would be our file descriptor, so we'd move RDI 0. RSI needs to be a pointer to our buffer. So this is where we run into a problem. What I want to do is move RSI something, and I'm not saying that you literally want this instruction, but you want this to be a pointer to like where I am. And then RDX, as we see here, is the count, which I just make it some big number. And then you do the syscall. For debugging purposes, I can't have question marks, but the idea here is, where is the instruction pointer right now? It is at this location. And if we were to look at the arguments that I'm about to pass into or trigger when I call read, I'm reading from standard in. Those bytes that I'm reading are going to 1337. And I am reading, let's print that as a decimal so that it's human readable, 1,000 bytes. Instead of reading to hex 1337, I want to read the bytes to where I am right now. I want to overwrite the region of memory that is being executed. Now, that I don't need to have a pointer to literally right here. It could be a pointer to somewhere behind. So like if we were to examine like 100 instructions at RIP minus, what's a reasonable number? Okay. So this is where I'm executing right now when read will occur. If I could somehow get RSI, which is the pointer where bytes are going to be read into, if I could get that to be anywhere, either where I'm currently executing or earlier, what I can do is when that first read call hits, I'm rewriting the assembly instructions. And so when RIP marches to the next memory address right here, right now before read, this says add byte pointer RAXAL. But when read actually hits, this can get rewritten before this gets interpreted. These bytes get interpreted as the next instruction. And so that concept of writing a first payload of shellcode that allows you to read in more shellcode is something that's called two-stage shellcode. I don't believe it's mandatory for any of these challenges, but it is something that you can absolutely do. And is a good strategy to try and employ. For the person who was asking about 12 byte, 6 byte, did we get you there? All right, cool. I didn't finish my discussion on why ESP is bad. Instead, I just went down this like tangent of dealing with the stack. Okay? So let's go back and look at this thing here where I had file, some file, right? And the question is why can't I use ESP? Because I said ESP is bad. We print RSP, and then we print ESP. What we see is RSP is a memory address, right? If I have to have Jeff for this to work, but if I VM map RSP, the stack pointer points to a very specific region of memory that is the stack. And we see this region of memory, the memory address is more than 32 bits. So if I were to try and grab ESP, what I get is 51EB2130. But that just drops off the higher order bits of RSP. And so ESP does not reference the same memory location. In fact, if I were to, I imagine this will explode. Yes. If I try and say, hey, where in this process is ESP? It doesn't point to anywhere. So when we're thinking about memory, there's tons of addresses that could exist, right? But some memory addresses, oh no, the camera, we've gone off the rails. Let's try and keep the camera on this side of the room. Okay. So when we think about memory in a process, we see that there are memory addresses that are valid. These are regions of memory that are mapped into that running process. And the stack is one of those valid regions of memory. If I try and access a region of memory in my shellcode that is not mapped into the process, which would be something like ESP here, we see that this is not mapped anywhere in here, and you'll get a seg fault. So you can't just randomly choose a memory address, and ESP is not a good enough location to, or ESP is not equivalent to RSP, and so you can't treat them the same way. Okay. Somebody says, all right, cool. So they got that. All right. Any other questions on shell coding? How am I on time? We're going to start at noon. All right. We're cooking. We're good. Can you make the challenge read more? Maybe there's another way. Yes, I showed or kind of roughly explained two-stage shell code. Somebody says, like, would something dot string then loading that into ESP work? Kind of like the example slides with bin sh. So there are a lot of example slides here. I imagine you're going. I strongly encourage you to not call exec in any of these. I don't call bin sh, do I? Like there's a whole other trap with dealing with bin sh and popping a shell. Okay, so here. This is doing the same thing that I did where I have a label and then I am loading that label's address rip relative into a register and then performing a syscall. I would recommend not doing this. This will execute bin sh, like it is valid shellcode. However, the shell that you get will not have root permissions for reasons that I feel like not going into at the moment. But I'm more than happy to explain at a later point. So there's the statement here from Twitch is like, I guess I'm just having, I need to do a lot of looking for info. You're struggling on how you can get flag onto the stack. So if you look at, I wish there was a way to rapidly iterate through these things. Well, I'm putting some file onto the stack. I did that here. And then at the very beginning, let's see if I can go up and find it. I was doing that same thing here where I didn't even put it on the stack. I just loaded the address directly into a register. And so it says, of course, with the restriction of 32-bit. Now your restriction, and somebody also says also symlinks, which we talked about in class, right? You aren't, for level 4, the first challenge that is assigned here, you aren't stuck with 32-bit instructions. What you're stuck with is don't have H bytes. And I don't know. We'll find out right now. LEA, RDI. Well, let's have a label. let's see if this does. Okay, so that does have an H byte in it. So you could, you're right that you couldn't do exactly this. But how else could I get, for instance, this is rip relative, so it's rip plus something. How else could I get rip into a register? This goes back to thinking about all the different ways that we could set a register to 0. How many different ways can I get something in? Get a pointer to some region of memory, right? Would be the question. Somebody here says use the stack, and that's exactly what I was going to demo before I somehow killed my Dojo instance here. I'll give it a minute. Well, you can push, like push RIP, pop RIP, right? I pushed 0, I could pop 0 right back off. Somebody says yours is down too. All right, so maybe I'm not following the admin chat right now since I'm streaming. Maybe they bounced all of the containers for some reason, and I just need to start up again. Yes. Okay. From pwn import star context arch AMD64. We're gonna GDB debug assembly. We're gonna push rip. We're gonna pop RDI. All right. It doesn't. It says, hey, you can't push rip. That is a problem. Right? So how do I get rip onto the stack if I want to try and do this like push pop? Well, can I move rip? I do need my comma. Okay. Says I can't do that. I have a really clever thing that I know I can do. You'll appreciate this one, or so someone will appreciate this one. So if my problem right now is that I can't get rip onto the stack, right? It's going to require a little bit of labels, and this is definitely more work than you need to do, because you can avoid using, you don't need to get rip onto the stack for any of this, but at this point I just want to do it. Then I'll show you some wizardry. So first thing I'm going to do is I'm going to jump to my call. My call is going to call label. And then I am going to pop RDI. And we'll throw a NOP in here. Somebody knows this trick. Okay, so you do know this trick. I thought you would appreciate this one. This is a well-known trick for getting RIP into a register. And so first I use a relative jump to get to this call. The call instruction, what does it do? It does two things. It pushes the saved return address onto the stack, and then it jumps to the label. And so now I jump to that label. And if we examine the address that is at RSP, and then we print RIP, we see that these are very closely related, right? If I were to examine, let's say, 8 giant hex at RIP, that doesn't work. Let's examine 8 instructions. Let's do it that way. Okay, cool. What we see is I pushed this address, which refers to this location, onto the stack. So then the first thing I do is I pop into RDI, And now if we print RDI, RDI is now a pointer to the region of memory that is just after this call. You don't need to do this for any of the challenges, but it's just an example of a more convoluted or more complicated way of abusing and misusing instructions if you understand what they actually do to accomplish your goal. This may come up at a later point. Foreshadowing. All right. Did I get all of the shellcoding things? Hey, I'm stuck on. I'm thinking about. I didn't show you exactly how to do it. How to get RIP in there or RSP in there. Like the simplest suggestion is just avoid the problem and use. Use symlinks to get to the stack. If you're trying to just get a pointer to RSP, what you should be able to do is push RSP, pop RSP. I don't believe that has... we'll examine like 4 giant hex at RIP. We see that there is no null byte here, right? Or no, there's plenty of null bytes. There's no H bytes. But the way that the class is like structured as a whole is like, I'll show you all of these technical things, but applying it is on you, right? Like you have to like be like, oh, I can grab this, I can grab that. How do I put this together and get the task done? One of the nice things, kind of looking at the vibes of the Discord chat, is that the people are really struggling on level 4, and then the people that have kind of made it past level 4, they're like, hey, all right, I these pieces are kind of fitting together. I'm knocking out, the next 2 or 3 levels, and then I get stuck, and then I knock out the next 2 or 3 levels, and I'm stuck. That's very common here because right now we're dusting off the cobwebs, kind of finding out what it is that we forgot over the summer or didn't pick up from 365. But once we close that gap, we should be able to move at a reasonable rate. All right, if nobody has anything shellcode related, I would ask that whoever it is that was curious about memory corruption, was there something in particular that you wanted me to hit right now live? For the record, as soon as I stop this stream, I'm going to record over that memory corruption slide deck. So in roughly an hour and a half, I will cover all of the high-level things. But if you're stuck on something in particular, I'm more than happy to get you unstuck right here, right now. I got to give it a few minutes or a few seconds for the Twitch delay here. Did the memory corruption person run away? They didn't believe I'd come back? Every once in a while, I'll admit, like I forget a question that was asked, and you got to hit me again. But I try quite hard to circle back and answer everything. Let me scroll up and see if I can find it. Push pop, LEA. Terminal, shellcraft, something default. I know somebody asked about memory corruption. I don't see it here in the chat now. Sorry for the brief lull. It's actually kind of nice. I try and speak over everything that I'm doing, but it wears me down. Let's talk about canaries and memory error stuff. They say not PIE. Okay. So let's see if I have. Let's see what we got here. So this was a example that I've kind of been chilling on. That is a buffer overflow example, kind of the basic memory corruption thing. I'll do like the dime tour here, and then if nobody has any follow up, it should time out reasonably well. As far as the 2 hour mark, because I've still got about 40 minutes I'm willing to throw at this. So kind of running through this with the source, what does this thing look like? I have a main function that says it's about to call a vulnerable function. We call the vulnerable function, then we say we're about to return from main. All right, pretty basic here. Our vulnerable function, I have a struct that has these values. Oh, this is, okay. This is not done. This is not a fully working example. See if I... And then I would have to say... struct s. See if the compiler likes that. As I was changing this. Yeah. Where's always false? Always false. That needs to be s always false. I was changing this to make it a little bit more. My struct has no member, always false. Yes, it does. Struct my struct s. Stack Overflow. Okay, Twitch chat says Stack Overflow says XOR EAX. EAX is the best way to zero out that register. My struct has no member, always false. It does have a member named always false. It's right here. Oh, yeah. I'd have to say s always false equals 0. All right. So hopefully I have a binary now named a.out. And it is pretty basic as far as what it does. Inside a vulnerable function, we declare this struct, my struct, which has a couple buffers, and it has a integer that is always false. That is what we call it. The reason we call it always false is because literally all we do is set it to 0. The vulnerable function says, what is your name? It then reads from standard in to this username field. And the username field we see here is 64 bytes in size. The read call will read up to 300 bytes. So we could definitely read in data, more data than was intended for this buffer field. That is a buffer overflow, right? The region of memory that we're intending to write to is smaller than the size of the potential write. It then prints out hello, whatever the username is, and then if, for whatever reason, this always false that is set to 0 is non-zero, then it will output always false is true. Assuming I compiled this correctly, there are a number of things that security features here that were disabled or enabled. To figure out what are the rules of the game when we're looking at binaries, the thing to use is something called checksec. And so if we type check sec. Let me go to my examples directory here. We check sec a.out. This should, good, tell us that there's no stat canary found because I compiled that with disabling it. The binary was compiled without PIE, which PIE is position independent executable. This has to do with how addresses are randomized. It is mentioned in the included discussions with Jan, and I'll also specifically try and discuss just these things here, canary, NX, PIE, in the video that I'll be recording after this. But no PIE means that, run path is weird. So this is an implementation detail of the dojo. If you are on a same Linux system, you will not get this weird Nix thing for run path. Just go with it. In general, we do a pretty good job of hiding this implementation detail. In a few places, it does still crop up and pop up. It shouldn't prevent you from solving any challenges. If you think it is, let me know. Odds are it is not. So this binary has no canary, which is the thing that's relevant for right now. Let's play around with this binary. What is your name? My name's Rob. It says, hello, Rob. And then it says it's about to return from main. Why do I have printf username read? Okay. Interesting. Why am I getting this nonsense here? What do you think? It wasn't an intended thing, but it's worth mentioning. So the string that is being read in here, I'm just using read. Read has no idea that what I am entering is a string. Read does not null terminate. It just takes bytes and puts them into memory. And so what's happening here is I say Rob, that writes to these bytes, and then what happens to be after it is a new line followed by an @ symbol and then an exclamation point before a null byte is reached. Because I'm not null terminating my strings. Somebody says, will Control-D help? Control-D wouldn't solve that. Control-D doesn't send a null byte. Control-D would prevent me from passing the new line character, but it would still print out until a null byte is encountered. So, if I run this thing, and as one of our great memes said here, we just ram a whole bunch of A's into it. I don't know how many of these are, but in theory, I'm going for more than 64. When do you think is more than 64? Maybe about here? I'm going to go for here. Okay, we seg faulted. So we definitely did more than 64. All right. So this goes back to, you could just sit here and punch A in the terminal, but we can use Pwn Tools Python, kind of get rolling on this a bit faster. So let's do that same thing. We'll start up an IPython session, or you would write a Python file. We'll say from pwn import star. We're always going to set our context, and we're going to use that same p equals process. In my case, this is a.out, and I can p interactive if I just want to play around with it, right? What is my name? My name's Rob. Okay, we're there. You'll see now that I don't have that at whatever. That's because when I did all these A's, what was in memory at that location has changed. It's non-deterministic because we're just printing out random bytes. The location of the null byte is the next null byte is non-deterministic. Now, I probably want to interact with this thing programmatically, so we can p-send the byte A, and let's send 64 of them. Okay. Now we get a about to return from main. What happens if I send 70 of them? Okay, we're about to return from main. If I send 80 of them, we're about to return from main. How about 100? We seg faulted. So I didn't set up this challenge correctly for what I wanted to do demo-wise. It'll be correct in the slides. I'll fix it up. But what happened here, because I wanted to overwrite that variable, but we're doing something else that's interesting. So why are we seg faulting? Does anyone have any ideas? Somebody says, I'm touching memory that I should not. Well, that's definitely true, right? And we know that from the source here. The username field is only 64 bytes in length. I'm passing in 100 bytes. I'm definitely writing past this username thing. The question is, what's on the other side of it? And we can use GDB to take a look at that. So I'm going to use the same thing we kind of saw here with shellcoding. I'm going to say P equals GDB debug, this binary. I'm going to pass in my 100 A's. We're P interactive. We are now inside this binary. Now I am interested in, I believe we have, what was it, vulnerable function. That does exist. So I can set a breakpoint at vulnerable function. We can continue. So we can take a look at vulnerable function in assembly. It's not too big. What I care about is what's happening at this read. So I'm going to set a breakpoint at vulnerable function plus 59. We can continue. So now we're about to call read. I don't care about stepping into read. I want to see what happens after read. The interesting part here, if we were to look at the man page for read, we see that the second argument is the buffer where the bytes are going to go. From calling conventions, we know that that is what is in RSI. So let's print RSI and let's examine, 4 giant hex at RSI. All right, it happens to be this right now. If I go NI for next instruction, so I'm stepping over this read call. We're going to let read do its thing, and we're going to get to the next instruction that is inside my vulnerable function. All right, we are there. You can't see it because it's black, but right here, it's black on black, but right here, it's call read. We just finished doing that. We are immediately after it. Let's examine the 4 giant hex at RSI again. We have 61616161. These are my A's. All right. If we scroll up a little bit here, we saw before the read, this region of memory had a bunch of other stuff. Well, how far did I go? How many A's did I really write? Well, I wrote quite a bit, quite a large number of A's. Now, I am inside vulnerable function, and vulnerable function was called by main. If we check our source here, right? Main calls vulnerable function. But when I look at what is the state of things as far as the debugger thinks, everything's messed up. Right? It thinks vulnerable function came from AAAA, which came from AAAA. Like we have definitely overwritten some like key data that is involved in the operation of this binary. Now, if you recall, there is something that is known as a function frame. This is where your local variables are, and that is stored on the stack. Inside vulnerable function, my struct is a local variable of vulnerable function. This is located on the stack. So when I overflow from username, I'm overflowing not only this variable, but if I were to keep writing, I could overwrite critical information that is stored on the stack. For instance, the saved RBP or the saved return address. So if I were to write, now this tells me where for my current frame inside vulnerable function. Where is the saved return address? Where is the saved RBP? And then where is the saved return address? And I can use that information to print out or examine what is the saved RBP. Well, the saved RBP, I overwrote that with my A's. It's now A. The saved return address is also a whole bunch of A's. So what the saved return address decides when vulnerable function returns, where does it go? If we were to, I can't. If we were to continue running until we get to vulnerable function plus 114. So now I'm down here at this ret. I'm about to return to what's supposed to be main. The ret instruction can be thought of as pop RIP. This is a preview of my stack right here. RSP is currently a bunch of A's. So when I perform this ret, I'm going to try and return to a memory location that is A. A is not a valid memory address. Therefore, we segfault. And memory corruption is about this concept. You may be corrupting a... Let's switch that around. Let's see if that makes life better for me. You may be corrupting something that is on another variable on the stack. You may be corrupting something that is critical data that is located on the stack that determines how the program behaves. There's a lot of information on the stack that can be corrupted if you can start writing out of bounds. So this isn't... this is what I wanted the demo to be. I had to switch the order of these structs because it turns out you can map C code to the literal layout in memory in a lot of cases. And so let's go back to this right here. When I send 64 bytes and we are interactive, we return from main. If I send 72 bytes, all we suddenly see always false is true. And the reason for that, if we were to... let me change my make file so that I have debug symbols. Cool. If we break at vulnerable function, I can print S. I can print S always false. Right now we see that it is hex 22, but that's because we haven't gone through setting this yet. So now S always false is 0. Right? And then that's why we are calling it always false. When we get to this read, we are going to, based on our Python code up here that is our exploit, we're going to send 72 A's. And those 72 A's are going to go into S username. Now I can print the address of S username. Right? We see that it is a character pointer array. What happens if I want to examine, I don't know, what's 60, 40? Let's go 40. 40 giant hex there. We can see the bytes that are located there. We can also print the address of S always false so that we have that here. So this right here is S always false. And this is where we begin taking in input. if I write 64 bytes, it's going to go 8, 16, 32, 64. There's enough space here for 64 bytes of input. As soon as I start writing beyond that, I'm going to corrupt the next value that is located in memory on the stack, which right here is S always false. We see that that's located at 5070, which is this right here. So now let's step to the next thing. Here, let's get to the read and get to the other side of it. So I'm going to step instruction. I'm now at the call to read. So nothing has really changed there. We step past it. We've now, I stepped into read. We'll fini to get out of read. And now if we examine that same stuff, that is the address of always false. That hasn't changed. We examine 40 giant hex starting at username, where that read started putting A's. We see A, right? And we did that for 16, 32, 64. And then this is the 64 bytes that was spaced for the username. This right here is overwriting always false, which is located right here at 5070. And so now what was expected to be 0 all the time is suddenly a non-zero value. And that's why if we were to continue here until it exits, we see always false is true, which if we look at the source code, that should never occur. Because in the intended operation of this program, it is set to 0 and it is never changed. Now, the nice thing about memory corruption and the memory corruption module is I did this in GDB on some random binary, right, that I threw together here. The memory corruption challenges will print out the stack for you. And so while I'm doing this in GDB, at least the memory corruption challenges have this pattern of like a 0.0 and then a 0.1. The 0.0 challenges will do the work of displaying their own memory to you. So you can kind of see this exact same stuff without having to mess about in GDB. But the 0.1 levels will not print out that help text. And so it will be up to you to use GDB or some other tool to reason about what's going on inside of it. Anyone have anything to ask about what I just did? This is not the only way to reason about memory corruption. There's a number of different techniques, which is what I will be recording as soon as I end the stream. Twitch has gotten a little bit quiet because I think most people are still on the shellcoding portion of things. I'll give it a moment for the Twitch delay. Somebody says they reason about memory corruption statically like a superior hacker. I don't know that is what the superior hacker does. It is a way to reason about it. I think it's a horrible way, personally. All right, with that, I don't believe we have any other questions. Time-wise, how did I do? So the problem with, so somebody says, I just prefer disassembling it. All right. So the problem with doing doing this stuff statically, and it may not be that big of a deal for this binary, but we can give it a try, is you end up with this scenario where the pointers may not be obvious, or the pointers that are being used. All right, you could get some pointer that is stored on the stack, and then it's loaded. The pointer is loaded from the stack, and then that's the pointer that's used. And so when you look at it statically, it becomes a bit of pain, and it can get confusing. So if we take a look at this in IDA, this tells me this has an offset of 4 hex 40, which is 64. And then if we take a look at where we are reading to, it looks like we are just reading to the address of S, since it's the first property there. This tells me it's at RSP plus 0. Does this tell me where this is? Yeah, see, this doesn't immediately tell me where the value is. We could go because it's an instruction, so IDA is actually treating it as a struct. Doing that. We could go to the assembly here, and if we go to vulnerable function inside of IDA, what do we see? We are calling read on RDI, RD, or what we care about is RSI, which are pointer door buffer. That's going to be RAX. RAX is RBP plus S. S is, does it tell me where S is? Okay, it tells me that S exists, and then what I want to know is where is always false. I can see the struct that always false is hex 40 in, but it's not nearly as like visually representative. So the statement from Twitch, because IDA is not my preferred tooling here, so if I double tap on the struct, it will show me the stack frame. I don't believe this is... Okay. That's fair. Right? Now I have my struct S, but I don't get the insight into how these are related. Right? I just have like S and then SR. Like I personally find using GDB in being able to, if you can verbalize your question, like you can phrase your question in English, I want to see this. Odds are pretty good that there is an equivalent GDB command, right? I want to stop at vulnerable function. Great. I want to examine 40 giant hex that are located on the stack, right? And then I can, as I step through, I can visually see how things change. For me, that is like amazing. And if you were just disassembling it, you could use object dump, but you get this same output here. Like I would rather look at, I agree, I would rather look at just raw assembly than IDA's pseudo assembly. So we're calling read. RSI is RAX. RAX is RBP minus D0. Okay, so this works. So it's something minus D0, and then the location that I'm interested in is going to be, it's not from this function, it's from the function frame above. So we have the disassemble main. To get an idea of where that is. Or does main? Oh, no, main sets it up here. Okay, my bad. So disassemble vulnerable function. So inside vulnerable function is where we're setting the setting always false equal to 0 because it's local. So right here is RBP minus hex 90. So we can think about this as RBP minus OX90 is somewhere on the stack. That's obviously a bad command. And then we start writing at RBP minus hex D0, because that is what is loaded into RSI when read is called. So that's the location of the read buffer. And so if we were to subtract those two offsets, since RBP, GDB really didn't like that. If we were to subtract OX 90 and we subtract OX D0 from it, we get, we have to actually, you take the big one minus the small one. We get hex 40, which if we look at it in decimal notation, we can still get that 64. And we're able to do that because this was pretty straightforward. We weren't throwing pointers onto the stack and then referencing those pointers, because then it becomes a bit harder to look up in the assembly. There's more steps than just finding this and then this, finding this number and this number for where they are there. Like personally, I'd rather use GDB or I'd look at raw assembly. When tools start trying to help me, I have a hard time understanding if they're helping me or their help is actually hurting me. Which is why I have the opinion that I personally have on these type of tools. Other people may have a very different opinion and a different workflow, but this is what works for me. So there's two different ways that we could find that. Someone says my opinion's wrong, but that's fine. Yeah, my opinion, my bias towards GDB is 100% the minority opinion for people that kind of work in this space. People tend to love IDA, and they spend a lot of time using tools like this. I like seeing what's actually happening. With that, if anyone has any last-minute questions, hit me. If not, I'm going to end the stream and start recording over those lecture slides. I've got about 3 minutes left on my kind of where I try and cap office hours time. As a unrelated ASU note, Monday is a holiday. It is Labor Day. That is a university recognized holiday. So while there are no 466 classes, there will be no classes whatsoever on Monday. So you can show up, but there'll be nobody there. That will apply to recitation as well. With that, I'll leave y'all. I appreciate you hanging out. Hopefully it was useful. Goodbye and good luck.